equations. So let's talk a little bit first about what a system of linear equation is. So after this lesson, you'll be able to solve a system of equations by graphing. And after this lesson, you'll also be able to identify the number of solutions in a system. So what is a system? What is a system and why is it messing with our linear equations? So a system is when many things have to work in harmony together. And they have specific outcomes and they have specific solutions. So you'll see this all the time in a science class. So a water cycle is a good example of that. We have moisture that comes from the ground, and it goes into the clouds. When it evaporates, it becomes rain, goes back down to the ground again, and the cycle continues over and over and over. Okay? So when we're dealing with a system of linear equations, we know what a linear equation is now. We've been graphing them. We know how to solve them. Okay? It's when two lines or two functions work together or touch when graphed on the same coordinate plane. So here's an example. We've got a graph here, represents some function, a nice diagonal line. We've got another function that you should recognize as a vertical function, right? And what we're saying is when those two functions get together and they cross, what is this point right here where they cross? That's what we're looking for. We're looking to see where that solution is. So there's three ways to do that. You have graphing. We can do it by the picture. You can do it by what's called substitution, and you can solve by elimination. Today we're only dealing with graphing. Okay? So flip to the next page. You notice on this section of notes, quite a bit of it is just explanation. So how many ways can straight lines cross? Try using your arms. If your left, I'm going to use my fingers. If your left finger is one equation and the right one is another equation, how many ways can you get them to cross? So if I never have them touch, then how many times are they crossing? They're never touching each other. They will never cross. So if they're next to each other, running parallel, they will never touch each other. So we can have no solutions. There's no time when my two fingers will cross. If we graph two lines on the same coordinate plane and they don't cross, we say the system consists of two parallel lines and has no solution. Okay? If they do not cross, then they have no solutions. We also know that at some point my fingers can cross, and what you're asking yourself is how many times do they touch each other? And they only touch each other once. So we obviously know that we can have our arms cross at any one point, so they can cross down at the base, they can cross up here, in the middle, they can cross different places. If we graph two lines on the same coordinate plane and they cross at one point, we say that that point, whatever it is the solution to the systems of equations, and we have one solution. What about when I lay my fingers on top of each other? Now I got to see how many places are my two fingers touching. And that could be really tiny points, right? So there's many, many places where my two fingers are touching. So if we have two graphs that when we graph them, they actually turn out to be the same line, then we say that that has an infinite amount of solutions, okay? And what it means is it means that the lines are actually the same. So as we go on, you'll see examples of all of these. And so these are your options. You either have no solution, one solution, or infinite solution, meaning many, many, many solutions. Okay? So let's graph some of these, or at least look at graphs, and we'll see what's going on. So remember, these are our options. No solution, one solution, or infinite solutions. So we're going to use this graph down here to kind of determine how many solutions each one has. They've already graphed the lines for us, and we can see which ones these represent. So let's start with this one. This is the line that represents y equals x minus 1. This line represents y equals x minus 3. This right here represents 2x plus 2y equals negative 6. This line is 2x plus 2y equals 4. And this line is 3x plus y equals 3. So they're all just functions. They all have names. All fine. So now we're going to look at each pair one by one and see how many times they cross. Remember, our options are none, one time, or infinite times if they're actually the same line. So let's look at y equals x minus 3, which would be this line here, and y equals x minus 1. So I'm looking at this line here and here. And I can see that if I go up, they have a crossing point right here. And they only are going to touch each other one time. So this has one solution. We don't even know what the solution is yet unless we look at the coordinates for that point right there. And I can see that my solution would be, the coordinates of that point would be -1, -2. Now, when you're solving by graphing, what you'd also want to do is plug your answers in here to see, plug your solution and see if that actually is in fact true. So our x coordinate is -1 and our y coordinate is -2. And we're just going to check, is that really true? So it's negative and our negative x function, so a negative negative is a positive, and 1 minus 3 is -2. That checks out. Now, it has to work in both of your functions. That has to be a solution to both functions. We can visually see that it is, but we can also prove it mathematically. So our y value is -2, our x value is -1 and -1. If I'm going to check that, -1 minus 1 is -2, so that one also checks out. If this is in fact a solution to your system, that point must be proven correct for both equations. It can't just be one. The system has to be proven correct. Okay, we'll talk a lot about that the more we go on. So let's look at our second set of lines. We have y equals 2x plus y equals -6. Yeah, it's plugged in. And we also have to look at this line right here, which is y equals -x plus 3. Well, look what happens. Those two arrows are actually pointing to the same line. So that is the same line. And so that means that it has an infinite amount of solutions. I can pick many, many, many points along that line. Let's look at the third example. We have y equals x minus 3, which is this line again, and 2x plus 2y equals 4. So I'm looking at this line and this line. And you'll notice, and so I'm looking at these two lines right here, and they don't appear to ever cross. They appear to be parallel, and that means that they will never cross paths ever. So they are parallel lines. And so there will be 0 solutions because there's never going to be a time where they cross. Okay, let's check the last one. 2x plus 2y equals -6. I'm looking at this line. And 3x plus y equals 3, which is this line. So I'm looking, oh, and there they have a point where they cross. Right there. So they have one solution. And that solution looks like it is at 3, -6. So we can check that solution again. This is my x coordinate, that's my y coordinate. So 2 times 3 plus 2 times -6 should give me -6. So let's check that out. 2 times 3 is 6. 2 times -6 is -12. And 6 minus 12 is in fact -6. Now remember what I said, that solution must work in both places. So let's see if that really does. My x value is 3. My y value is -6. 3 times 3 is 9. Minus 6 is 3. So that is the solution to that system. Okay, let's do a little practice now. So I'm going to do a couple of these with you, and then I'm going to want you to do some independently. So let's start with number 5. So I'm going to graph both of these lines on the same coordinate plane. Okay, so let's start with the y equals -2x plus 1. I begin at 1 because that's my y-intercept. My slope is -2, or -2 over 1. So from that point, I go down 2 and over 1. Okay. And for my second equation, on the same coordinate graph, my beginning point is at -1. And then I'm going to go up 3 and over 1. Okay. So I will see that I do have one solution. We're just determining how many solutions our systems have at this point. We're not even figuring out exactly what they are, just how many they have. So this has one solution. Okay. Let's go on and do number 6. So my first equation is y equals negative 2x minus 1. I begin at negative 1. Because that slope is negative, I know I'm going to go downhill, so I'm going to go down 2 and over 1. Or I could have gone up 2 and to the left 1. So there's that equation. Let's go ahead and label these actually while we're at it. So this was y equals 3x minus 1. This was y equals negative 2x plus 1. This is y equals negative 2x minus 1. And let's graph this second equation. So I begin at 2, and then my slope is also going downhill. So I need to go down 2 and over 1. Something similar about those lines, because they are parallel, so they have no solution. I want you to think about why those two graphs may be parallel. I just want you to ponder that question, and we'll talk about it when the farther we go on. Okay? I want you to graph 7, 8, 9, and 10, and then come back and check your work. Okay, so I'll graph these quickly, starting at 0. My slope is up 1 over 2. And the second equation, I would begin at negative 1. And I can either go up 2 and 3 to the left, or down 2 and 3 to the right. So those lines are going to cross right there, so it will have one solution. Number 8, I begin at 6, 1, 2, 3, 4, 5, 6. And my slope is negative 2, so I'm going to go down 2 and over 1, all the way down. And my second equation is y equals 2x plus 2, so I'm going to begin at 2 and go up 2 over 1, up 2 over 1. So again, that has one solution. Okay. Number 9, for my first equation, my y-intercept is 3, and from there I'm going to go up 2 and over 3 because that's my slope. My second equation, I'm going to begin at negative 2, and I'm going to go up 2 and over 3. My parallel lines that are never going to cross, so I have no solution to that line. Okay. And lastly, for 10, what do you notice about those equations? They're exactly identical to each other, so I'm actually just graphing one line. And I would essentially be regraphing that line again, which means it's the same line, and it has an infinite amount of solutions. No matter what numbers you plugged in, every solution is on that line for both equations. Okay, make sure your graphs all are done properly and you're understanding those concepts right now, and then we'll move on. Okay. So now we're going to kind of do the same thing. I would like you to do this practice on your own, these 3 problems, and then we'll come back and check them. So you're just using the graph, this is like we did 2 pages ago, to check to see how many solutions they have. So do that now and then come back and check your. Okay, so first one, I'm looking at y equals negative x plus 2 and y equals x plus 1. I'm going to see that they cross at one point and they have one solution. Number 2, I'm looking at the y equals negative x plus 2 line and the 3x plus 3y equals negative 3 line, which are these 2 lines here. And I find that they're parallel, meaning they're never going to touch, so they will never have a solution. So that's a no solution. Lastly, I have the 3x plus 3y equals negative 3 line and the y equals negative x minus 1 line. They are in fact the same line. They're pointing to the same line. So I have an infinite amount of solutions for that one. Okay. Let's do a little bit more practice, like you do the 3 problems down below. And tell me again how many solutions they have. Do number 4, 5, and 6, and then come back and check your work. Okay, I'm going to graph these now. So y equals 3x minus 4. I'm going to begin at negative 4. Then my slope is 3, so I go up 3 over 1. And my second graph is y equals negative 3x plus 2, so I begin at the 2. And I go down 3 over 1 right there. And that is going to have one solution. Those 2 lines cross at one point, and it looks like that point is at 1, negative 1. We'll do a lot of checking solutions to these problems in class. So, okay, number 5, y equals 1/3 x plus 3. I'm going to start at the 3. From there I'm going to go up 1 over 3. And so that's my first graph. Second one, I'm going to begin at negative 3. And because that's a negative 2/3, I know I'm going to go down 2 and over to the right 3, or I could go up 2 and to the left 3. These lines you need to continue all the way out to see what that behavior is going to be, if there's lines that are going to touch or not. These lines do touch, and you would have one solution. And it looks like that solution is out at negative 6, 1. Okay, lastly, I want you to look at those 2 equations and see what similarities they have, and then see what the resulting picture looks like. I just want you to think about those 2 things. So, first equation, I'm going to begin at negative 2. My slope is 5/4, so I'm going to go up 5 and over 4. Second equation is at 5/4 x minus 1. So I'm going to begin at negative 1, and I'm going to go up 5 and over 4. Okay. Those are parallel lines. Parallel lines we know will never touch. They run alongside each other but never cross. They have no solution. So I want you to think about the similarities I see, and that both of these equations have the same slope. If they have the same slope, they will be parallel lines, because that means they have the same steepness. They lean at the same angle, right? They're running exactly the same rate of change. Okay, good. So we'll do a lot more practice on graphing in class, and the other ones that we're going to graph are now not equations, but think about the other things that we've been graphing, and those are inequalities. So remember, the only thing that's different between graphing an equation and graphing an inequality is our shading. So one thing that I think will really help you when you are graphing inequalities is to either have 2 different colored pencils or 2 different colored highlighters, actually. The highlighters you need to be careful of because they do bleed through the paper. So, but 2 different colored pencils or a pen and a pencil, that helps too. So remember that when we are graphing inequalities, now instead of one line, we have a line that either includes those solutions or excludes those solutions, depending on whether it's a greater than, less than, or a greater than or equal to, less than or equal to. And our shading depends on whether we have greater than or equal to, or less than or less than or equal to. So you're not going to have just a line of solutions now. Now you're going to have a whole range of solutions. Where the pencils help is that one will be represented by one color, one range. The other will be represented by the other color. And where those colors combine, that is going to be the solution to your entire system. So let's try one, and you'll see what I mean. So 3x plus y is less than 2. Now, we could do this in one of 2 ways. I'm going to go ahead and move that into slope-intercept form. And now that we've been practicing that, we know that that means our x term needs to go to the other side and switch signs. So that would be y is less than negative 3x plus 2. My second equation is also not in slope-intercept form, so I need to move the 1 over to the other side, and that's going to switch sides. So that is y is greater than or equal to x minus 1. So I'm going to graph this in blue and this in red. We'll see what happens. So y equals negative 3x plus 2. I'm going to begin at the negative 2, and I'm going to go down 3 and over 1, all the way down, or I could have gone up 3 and over 1 to the left. I know that that needs to be a dashed line because it's only a less than, not a less than or equal to. And because it's less than, I'm going to go to my intercept, pick a number less than 2, which would be anything below that. So that is going to get shaded right here. Okay. Now I'm going to graph my other line. I'm going to begin at negative 1. My slope, if there's nothing there, I know that it's a 1, which is the same thing as 1 over 1. So I'm going to go up 1 and over 1. Up 1 and over 1, all the way up. That's going to be a solid line because it is greater than or equal to. And because it is greater than, I'm going to shade everything above that line. So now you kind of see why the colored pencils really help. This was my blue region. This was my red region. The region where they both occur is going to be my solution to the system of inequalities. Okay, so it's everything in this region that is colored by both colors. Okay, now I just need to check to see if these are in fact solutions in that system. So we're going to check that. 0, 0 is right here. That's in that system, so we're good. 0, negative 4 is a solution to the blue, but it is not a solution to the red. It's not a solution of both. So the 0, negative 4 is not going to be a solution. I'm just checking to see that these points are in my doubly shaded region. So 1, 4 is there, which is in my red, but not in my blue. So that one doesn't work. And negative 3, 3 would be here, which is a solution to the system. Okay. I will tell you that normally with inequalities, it is much easier to have them in slope-intercept form than it is to have them in standard form, so I would recommend changing them before you do anything. So let's kind of lay both of these out and get them into a more useful mode. Okay, so for slope-intercept form, I need y by itself. I'm going to move my 8x over to the other side. So I get 4y is less than or equal to negative 8x plus 12. Then my second step is to divide everything by 4. So I have y is less than or equal to negative 2x plus 3. So I'm going to make that my blue line. And I would start at the 3, and I'm going to go down 2 over 1, all the way down, or up 2 to the left 1. That's going to be a solid line because it's less than or equal to. Decide where you're going to shade. Less than is everything below that line. If you're not sure, pick a number that's less than your intercept, so I know that 0 is less than 3. So this is the area I need to shade that in. For my other line, I almost have y by itself, but that 2 needs to go over to the other side. So I'm going to subtract it from both sides and get y equals 1/2 x minus 2. That's going to be my red line. So I'm going to begin by graphing at negative 2. Then I'm going to go up 1 over 2. Up 1 over 2, all the way up. That's going to be a dashed line because it is less than. And it's going to be everything less than that intercept. So something smaller than negative 2 would be negative 5. So it's going to be everything down in this region here. So all of my solutions are going to be within this region. And they go on out forever. There are many, many, many solutions to a system of inequalities. So let's check. So 0, 0 right in the middle does not belong in my solution region, so that's not one. 5, -1 is way out here. That's not a solution. 0, -4 3 is in my solution region, so that one's good. And -2, -3. Now this you need to be careful of. That line right there is dashed. So even though -2, -3 is on that line excludes all of those values. So that would not be a solution. If you had a point on the blue line, that would be a solution because it's a solid line, which means all of those solutions are included. Okay? All right, go ahead and I would like you to attempt the last two on your own and then come back and check your work. The first thing you're going to need to do is change those into slope-intercept form to make it a more feasible problem. So do that now. Okay, so let's change our equations first. We have -3x plus 2y is greater than or equal to 2, and -4x plus y is less than 3. So I need to move my x term. When it moves to the other side, it switches signs. So I would have those cancel, and I would have 2y is greater than or equal to 3x plus 2. And then I need to divide everything by 2. So my slope-intercept form of that equation, that inequality would be y is greater than or equal to 3 has x, 2 divided by 2 is 1. This one is almost good to go. I just need to move that x term over to the other side. And when I do that, that is going to change signs, so become positive. So y is less than 4x plus 3. I'm going to make the first one blue, second one red. So my first one, I'm going to begin at 1, and then I'm going to go up 3 and over 2, or down 3 and to the left 2. That will be a solid line. And I'm shading everything above that line because it says greater than or equal to. So that's going to be on this side. For my red line, I'm going to begin at the 3, 1, 2, 3, and then my slope is 4 over 1, so 1, 2, 3, 4, and over 1. Or I could go 1, 2, 3, down 4, and to the left 1. That will be a dashed line, and it'll be everything less than that line. So even though that line's really steep, I still want you to put your pencil on your intercept and think of a number that's less than 3. So 0 would be less than 3, so it's everything on this side of the line. This time our region is really kind of skinny, but it's still your solution region, and that would keep going on out forever. Let's check our solutions. 0, 0 is not in our region, so that is not. 3, 5 would be 3 and up 1, 2, 3, 4, 5. So here's a perfect example. Because that line is solid, that is a valid solution because we know that all the solutions on a solid line are included. All the points on a dashed line are not included. Okay, 2, 4. So 1, 2, 1, 2, 3, 4. Again, on that line, so that is a solution. And 0, 3. 0, 1, 2, 3. That is not. All right, last one. So now we've got a y is less than or equal to 3. I want you to think about what kind of line that is. And that's going to be our blue line. So this is the same as y is less than or equal to 0x plus 3. So if we graph that, we're going to begin at 3. You should know by now that that's a horizontal line. It's going to be a solid line. And it's going to be everything less than or equal to that line. So anything less than 3 would be below the 3. And look just like that. Our second equation is not quite in slope-intercept form, but I just need to move my x term. Sorry about the bell. And when it moves to the other side, it's going to become negative. So it'll be y is greater than negative x plus 1. That's going to be our red line. So we begin at 1.
False alarm.
And then we go down 1 and over 1. Sorry for the interruption. That's going to be a dashed line. And it'll be everything that says greater than, so it's going to be everything above that line. Our region right here will be our solution region. So let's check our solutions again. 0, 0 right there is not in my solution region. 2, 2, 1, 2, up 2. That is in my solution region. 0, negative 4. It's a solution for my horizontal line, but not for my y is less than or equal to 3 line, but it is not a solution for the other, so that is not. And then 5, negative 1, 1, 2, 3, 4, 5, negative 1, that is in my solution region, so that is a solution. All right, I would really like you to bring colored pencils on Monday and Tuesday. That'll make graphing inequality so much easier and a little bit more festive. And we'll see you then. Thanks.